Hello and welcome. Hey, thanks for coming, everybody. We're really excited to have the folks from Microsoft down, Anders and the rest of the team. He's going to talk about where TypeScript is and maybe a little bit about the future. And please give him a warm welcome to Anders.
Thank you. Thank you. Let me just put this one up. Yeah, we need to, I think Brad's pushing the button there so we can see some slides. So my name is Anders Hejlsberg. I'm a, a technical fellow at Microsoft in the developer division, where I work on a variety of things, including the TypeScript project. I also worked on C# and .NET and so forth. But today we're here to talk about TypeScript, which has been out for a couple of years now. It's actually about our second anniversary of going public. TypeScript is about addressing this problem, basically. You know, a problem that we hear increasingly more and more from customers and internal users, that writing really large apps in JavaScript is hard. And the reason people write these large apps, I think, is, as you all know, JavaScript is really the only cross-platform game in town now. Even Java, that was conceived to be cross-platform, isn't really, because you can't run it on iOS, for example. And so people write increasingly larger JavaScript apps, and JavaScript was really never intended for writing large apps. And in fact, it was conceived in 3 weeks by Brendan Eich, and I think the intent was maybe you'd write like 100 or maybe up to 1,000 lines. And now people write hundreds of thousands of line apps in a language that arguably have no concepts for structuring large code bases. No classes yet, at least, or no modules, no interfaces, and there's no static typing at all. It's a purely dynamically typed language. And that's great for little stuff, but the bigger it gets, the harder it is to manage these large dynamic code bases. Because if you think about what it is that powers the intelligent IDEs that we as programmers that rely on every day, at the core of most of it is static typing, or the ability to reason about the code in intelligent ways so the IDE can deliver invaluable things like statement completion, go to definition, find all references, refactorings that are known to be safe. That just gets super, super hard in big dynamic code bases. And gradually, once you reach some tens of thousands of lines, they basically become read-only, because no one dare touch anything in here, right? Because who knows what's gonna fall over. So as we set out to work on this problem, we thought, wouldn't it be nice if we could add to JavaScript these things that are missing, like classes, modules, interfaces, and static typing, but add it in a way that doesn't mess with the core value proposition of JavaScript, that is, the ability to run anywhere on any browser, on any host. And that really, in a nutshell, is what TypeScript is. It's a language for large-scale JavaScript app development. In a sort of more technical sense, it is a typed or statically typed superset of JavaScript that compiles to plain JavaScript. So TypeScript itself is written in TypeScript and therefore compiles to plain JavaScript. And so the TypeScript language and tool set and the code it generates runs on any browser, on any host, on any OS. And the whole project is open source, and we switched to hosting on GitHub in June, and it's great. We're getting a lot of community participation. We do all of our development processes in the open. So that's sort of in a nutshell what TypeScript is. Basically, it starts with JavaScript. So it's important to understand that TypeScript is not a new language or a different language. It is at the core of it JavaScript, but it's JavaScript with type annotations and the ability to declare types. So what it adds is types, including generics and all sorts of other fun stuff. And then powered by that is excellent tooling that does things that you just couldn't do with purely a dynamic programming language. But when you compile, it all goes away and you're just left with JavaScript. In fact, you're left with what I would argue is idiomatic JavaScript that looks like a human wrote it. We don't actually mess with your code or inject code. We don't have a runtime library specific to TypeScript. The code that you get is the code that you wrote minus the types. That's basically how it works. So, with that said, I'm going to spend most of this talk actually demoing the product itself live, and then from that you can sort of see how it works. What I have here is Visual Studio with the latest version of TypeScript in it, and we're just going to write some code and then see how the system works. I'm going to start just with some plain JavaScript here. There's a function that sorts an array of things that have a name property, and as I said, to begin with, any JavaScript is TypeScript. So you can just copy and paste or rename your files to .ts. And to begin with, we know no more than a dynamic system. Well, we know a little bit more, but if you start like hovering around in the IDE here, parameter here, A, but we know nothing about it, and there are no calls, there's nothing. Just A has type any. And that in turn means that you can, on A, invoke any method you care to, and if I say A dot, well, sorry, got nothing at this point, right? So clearly this function is a function that sorts an array. We do know some things, though. We do know that you've declared a function sort by name, so we can at least show you that. But you can pass it anything you want, including something that's not going to work. So it sure would be nice to be able to annotate this and say, well, I know that A is supposed to be an array. And we're not the first to get this idea of annotating your code. You guys have a product called Google Closure, right? That allows you to write, I'm not sure if I wrote it the right way, but something like that, right? Where you put annotations in comments. That works if your design goal is to not at all mess with the stuff outside the comments. But comments are not a particularly great place to host a type system, at least syntactically. It doesn't look as great, and it's an alternative would be to actually allow you to annotate the code directly. So here I could say, I know that A is an array. I don't know an array of what, so it's an array of anything. But I can simply add that annotation, and then when the compiler compiles my code, it just takes away the annotation. So the annotation is there purely for development time. It has no cost at all at runtime. But once I do that, well, then we now know that A is an any array. And we know that the slice function is a thing that returns an array that has the same type as the thing you invoke it on. And therefore, we know result is an any array, and since we're returning result, we know that sort by name now is a function that returns an any array and takes an any array. And we can now validate down here, and we can say number is not an any array. So you add annotations, and things gradually start to light up. And you'll note that a lot of it gets inferred. I just added one type annotation, but we found out a whole bunch of stuff by flowing the types. And you'll see that it's actually fairly minimal how many annotations you have to add, and because we do a lot of inference. Also, now that I know that A is an array, when I say A dot, we can show you all the methods of an array. We can give you statement completion and so forth. But of course, there are things we still don't know, like result.sort takes a callback function that's going to present the elements of the arrays in pairs, and you're supposed to compare them. But since we don't know what the types of the elements are, all we can know about X and Y is that they could be anything. And so we're sort of gradually typed. We're half typed here, but we're not fully typed yet. And that means there might be bugs that we don't find. But we could try to say more. I mean, here obviously we're sorting on a name property, so we could declare a thing that has a name property, and then we could say that our thing is an entity array now. And an interface declaration in TypeScript is really just stating that here's a thing that has the following properties. We're not stating anything about how it came about. It could come about by you just assigning some properties into an object literal, or it could have come about by you creating a class or whatever. It's structural, meaning that anything that has a name property is an entity, including some other definition called so our type system is structural, not nominal. Now, you'll see that now that I said that these guys are entities, well, now we know that result is an entity array, and we know that sort is going to present two entities here, and we know that an entity has a name property, and we can give you statement completion there, and then we know that name is a string, so we can give you statement completion again, and then you'll see here that we actually also discovered a bug in this dynamically typed code. Someone was calling local compare, but what they probably meant to do was to call locale compare, but just typed it wrong. So now we can fix the bug. It's always better to fix it before the space shuttle flies than in flight, right? So, okay, so now let's try to, now that we've actually typed everything or given types to everything, let's try to introduce another thing called name. Now, one of the things that's hard in dynamically typed code is, let's say you have 50,000 lines of code, and you're using a property called name in a bunch of different places. And now for this object here, I need to change this name property to be something else, but I don't want to change all the other places, right? That's something that is insanely hard to do in a dynamically typed system. You may think you have unit tests that cover it all, so but we find with regularity that people that swore they had unit tests to cover it all didn't quite have unit tests that covered it all, because there's nothing that checks it for you, right? So here, I can now, for example, go to my interface and say, let me rename name to entity name, for example. And you'll see that even though there's another thing called name, we don't rename that, because through types, we understand what the difference is between the different things called name. And that's where this stuff starts to add value. Obviously, a little program like that, it's not hard, but the bigger it gets, the harder it gets, right? And eventually, it's, like I said, it becomes read-only. Okay, so let me try to add a few more. Let's add a price. Call a number here to our entity, and then let's try to create an entity. So we allow you to put type annotations on code that you're writing, like this. Here, for example, I'm saying E is an entity. And you see that it complains that we're missing some stuff. We're missing the name property and the price property. We actually can give you statement completion here through what we call contextual typing. We know that this object literal is getting assigned to an entity, so we can flow the types the other way and show you what should come here. And there we should have a name property, let's call it a hammer, and a price of $5.95, say. And now the error goes away because the type checker is happy. But again here, it's all structural, really. It's not like I had to new up a class or anything. I just said, you know, it has to have these two properties. If I go add, say, an in-stock property.
Anders?
Yeah.
Can I ask a question?
Yes.
So,
Yes. Give me 1 second. I was going there right now. Let's say I now add an in-stock property here that may or may not be there. Okay. But if it's there, it has to be a bool. Right now, it complains that it's not there. I could then either go add it, or I could indicate that in stock is optional by adding a question mark to it. And now I've said, if there is an in stock property, it must be of type bool, but it is okay for it not to be there. So if I say in stock here, :5, for example, you'll see that it complains in stock is incompatible. You can't assign a number to a Boolean. Can you read the font here? Is it? Okay. But if I change it to true, then things are happy. Okay. Now, you can, of course, declare other things. We could declare methods, like, say, set name and get name here. Now, since they weren't marked as optional, I must implement them. So let's say set name. Actually, let's do get name first. Get name colon function return this dot name and set name function that takes string. And in here now, if I say s dot, you'll see that we know stuff about s. And this is, again, contextual typing in action. We know that you're assigning to an entity. We know that entity has a set name property. We can flow that into, contextually into the expression that you're initializing with, and then we can contextually type this argument in case you didn't give a type annotation. And you'll see that this works great as you're like doing these dotted together pieces of code with callbacks in JavaScript. We can flow all of that stuff, and you don't have to put type annotations in a whole lot of places. So here, this dot name equals s is how we would complete that piece of code. Yes?
So what if you have to have two identical types? How does it pick which one?
Yes. So the question is, what if you have two identical types? What is it? It doesn't care if you have. It's all by structure. If the two are structurally equivalent, you can use them interchangeably, and one is assignable to the other. So it's truly a structural type system, not a nominal type system. And that means you implement an interface if you have all the properties that the interface says that you must have. It just happens it just happens automatically. I think we somehow, okay, there we go. Go back to the code. Cool. You don't want to look at me. You want to look at the code. Okay, let me try to shorten this down a little bit, and then let me grab this code and move over to the browser and try to play with this in the TypeScript playground, which I have over here. So if you go to our site, the TypeScript site, there's a little playground where you can type in code and see the output JavaScript code. And one thing you'll notice is it's your code. It's exactly the code you wrote. I mean, they're literally, the method bodies are identical, except the type annotations are erased. That's the only thing you see. So here, all of the type declarations went away. The type annotation went away here. But other than that, it's exactly the same code that comes out on the other side. I'm going to try to actually make this code run just for fun. So let's go back and let's pick a set of products here. Maybe let me just scroll this up a little bit here so you can, well, there. And then let's try to use our sorting function on those products. So we'll say var sorted equals sort by name of products. Now you noticed here that I get statement completion and hovering help and whatever. I can hover over here and see products is an array of things that have name, price, and ID. This language service, the thing that provides all of that help, is actually part of the open source TypeScript project. So the compiler isn't just a batch compiler. It's really more like an API that allows you to ask intelligent questions about the code. It can produce an AST for your code to allow you to do code navigation. You can go in at any point and say, what is the type of this thing? And we will lazily evaluate just enough to figure out what the type is here, so you can do statement completion and so forth. And it's all written in TypeScript, so you can use it anywhere. And so here we're actually using the very same compiler hosted in the browser in our playground. Okay, so if we look at what's happening here with our sort function, so sort by name takes entities, and therefore it returns entities we've inferred. We're passing it things that are entities because they have a name property, but they also have other properties, right? And so if I come out the other side here and say products dot not sorted. If I say products, I get all of the properties. If I say sorted, I only get the name property, because we've inferred that they're entities. But really, there's something a little bit funny about the way we've added typing to our sort by name. It isn't actually true that sort by name takes entity array and returns an entity array. it's true that it takes an array that must have a name property and returns an array of that same type, right? And that we can represent by writing it using generics. So we could say that sort by name is a thing that takes a T array, and then from that we can infer that it returns a T array. And now, since we passed in something that has 3 properties, well, they come out the other side now with the same type. So generics here allows us, it gives us a higher bandwidth conduit to flow types. And that's really sort of the purpose of generics in TypeScript. It is to flow types with fidelity around graphs of connected objects, right? Now, you will note, though, that now another problem showed up. Here, it starts complaining about the name property. And it rightfully does so, because we're using a name property on a T. But T could be anything, including something that doesn't have a name property. So we need to constrain our T, which we can also do. So we can say T extends entity. And now things are happy, because now we know that X has a name property, but we will still flow out of sort by name a T. And so down here, we still get the right type for the elements coming out, right? So that, again, is just sort of why generics are important. Because you might go, generics in JavaScript, that sounds insane. Why would you want the generics? But look at the output code, right? There's no trace of this generic stuff anywhere. This is all an illusion that exists at development time to just give you a high fidelity way of flowing types around in your code. Just for kicks, we could try to add one line here that actually JSON stringifies our result, and let's try to run it, and we can see that yes, it sorts things by their name properties. Now, let's try to make it a little more advanced, this example, though. Let's instead of sorting by a name property, why don't we have a function that has a callback that allows you to want to sort by. Can also do that. So let me pick one of those here. Let me try to change this here to look like this instead. So now we have a sort by method that takes an array of T's, and then it has a callback function that calls back presenting a T, and you're supposed to then pick a value out of that T that you want to sort by. And then during the sort, it calls this callback function to pick out values. So now, call sort by of products, comma, and now we're supposed to write a callback here. And I can write that as a lambda, and this is where an example of where we polyfill ECMAScript 6. So I just say, call it x dot, and you see that we do statement completion here. We know that we have flowed the T through products into your lambda, and can now show you the properties you can pick from. So we'll pick a name property here. We can try to run this and see that they're sorted by name. We could instead try to pick price, for example. Try to run that, and now it sorts by price. So it works. Notice how in the generated code, we actually turn it into an inline function, which is part of what fat arrow does in ECMAScript 6. It also has different semantics around capturing this, which we understand and will generate the right code in function closures and so forth. But basically, part of the purpose of TypeScript is to give you static typing. Another purpose is to polyfill those features that are missing in ES3 and ES5 that are coming in ES6. And so all of the extensions that we have are aligned with what's happening in ECMAScript already. And we're currently working towards full fidelity with ECMAScript 6, which we'll probably reach by spring-ish. Okay, let me just try to grab this code and bring it back to Visual Studio, and then just show you some of the latest features that we're working on, which is union types. and tuple types. Tuple types are already in, but we're doing union types, or we did union types there in the master branch right now. It's very common in JavaScript APIs or objects to have properties or parameters that can be one of multiple things. For example, a sort method here might take either a callback function or the name of a property as a string. That's one pattern. Another is you can pass it, a configuration object either as an object literal or as a string or as a number or whatever. Up until now, we could not express that, but we now allow you to write union types. So you can say this must be a string or an item callback. And you use the OR operator for that. And now a few things happen here. Well, first of all, let's try to call this key. And now it's going to complain that we don't have a callback. So let's say var callback equals key. It's still going to complain because you can't call a string or function because it could be a string, right? So you got to do something first to sort of distinguish between the cases. And there are patterns in JavaScript that are pretty common. One would, for example, write here type of key triple equals string. If we have a string, then, well, now we can make a callback function that we could use then. And so let's make one where we pick out the key. Otherwise, we know we have a function, so we'll just pick that function. Now, note how the types all worked out here. If you hover here and see key, it has type string or callback function. But if you hover over here, it has type string. And if you hover over here, it has type callback function. Because we understand what type of does. And we understand that a type of triple equals string will remove string, or will select string or remove string from the available types in a union type. And so we can reduce the type, call it narrowing under a type guard. And that's what you're seeing in effect here. Yeah? Yes, so the question is, must I compare to the literal string, or could I have a function that says is string or whatever? So one of the next things that we're looking, so right now we analyze type of and instance of. We are also likely going to do discriminated union types. It's very common to have a kind field that can be, let's say north, south, east, or west as a string literal, right? And then based on that, you can know the rest. We can discriminate on things like that because we actually allow you to just define string literal types that can be one of a set of values. We use that for overload resolution. But then finally, the thing that we're likely also going to do is what we call user-defined type, where you define a function and you just designate that function as the one that, trust me, if you pass it, if you call is customer and is customer says true, then whatever you passed is a customer. And we'll fold that into the type system as well. So that's one of the things that likely will show up in the next few months. But right now, we at least cover the typical patterns that people use in their JavaScript code. And of course, we cover all the various funny cases. If you write it the other way around, then you can flip the arguments and et cetera, et cetera. You could write it as an if statement. We'll likely also allow you to write them as switch statements and so forth. So, okay. That is, well, let me show one more thing. You saw how when I say a dot here, we show this statement completion. You might wonder, where did that information come from? Is that just sort of built into the compiler, or how do you know what these types are? We can actually say, go to the definition of slice, just press F12 here, and boom, it jumps me into a file called libDTS, which is a declaration file that is included in every compilation. This particular file, you could think of as the header file for the JavaScript runtime library and the entire HTML DOM. It's it's a file that exists purely to provide all the static type information for the JavaScript runtime library. It adds 0 cost at runtime because it just goes away. It has nothing but declarations in it. But with this file in hand, you now have a synopsis, if you will, of here you see 14,000 lines of JavaScript code that you otherwise are supposed to memorize, right? When you're writing in JavaScript, you're supposed to know what all these functions are because your IDE sure as hell doesn't. Now it does, right? I mean, and this is where static typing really helps, right? It's just ridiculous to sit there and manually look up what all of these functions are. This is just something that the computer should know for you, right? Now the cool thing about these is that there's nothing magic about these declaration files. Anyone can write them, and you can write them for existing JavaScript frameworks. And what we've seen shortly after TypeScript went public is organically in the open source community, this GitHub repository called DefinitelyType sprung up. And it's become the place that collects all of the declaration files for all of the popular JavaScript frameworks. And I challenge you to find a framework that doesn't have a declaration file there now. There's more than 600 frameworks that have coverage. There are over 600 committers in that repository, super active. And the quality of a lot of this static type information collected in there is pretty darn high. Like things like jQuery, Angular, I mean, they all have declaration files. And now we're seeing tools that automatically provision your projects just by fetching the declaration files from DefinitelyType and so forth. So that's all pretty cool. Was there a question over here? Yeah?
Question about the union type.
Yeah.
What type consist of?
Yes. I mean, so there are cases where we can't. Okay. Oh, sorry. What if a union type is like 2 different functions that accept different arguments, for example? Well, there are different ways to write that. Typically, you would write those as an object that has an overloaded function with multiple call signatures, which we can then disambiguate. If through union types you get 2 objects that you can't actually, with a type of or instance of test, tell which one it is, well, then you could use a user-defined type guard, like I talked about. It's not implemented yet. Or you can simply put a type assertion where you do your test and then you just assert that it is now this type by casting it. And the cast then goes away in the compiled code. So it's really just there to guide the type checker, if you will. I'll show you an example of that a little bit later. Okay, so that was, let me try to go back and show some of the other polyfilling that we do. One important one is classes. So I could write myself here in the playground class point with x colon number and y colon number. Sorry. Polyfilling means implementing features that are coming in a later version of the language in a down-level manner using features that exist in the older version of the language. So classes are coming in ECMAScript 6, but you can actually emulate classes using idiomatic JavaScript code and certain patterns that correspond exactly, or almost exactly, to what ECMAScript 6 would do. So here, for example, if I declare a class at the core of it in JavaScript is just a constructor function. We also use the pattern of putting it in an immediately executed function expression here to give us an isolated scope for local variables and so forth. But now that I have a class, I can say var p equals new point, for example, and then we know that p has an x property and a y property that I can assign to, for example. So, whoops, there. Okay, of course I might want to pass them as arguments to my constructor, and if I try to do that, then we complain that there is no constructor, but I could go write one. So constructor of x colon number, comma y colon number, say, like so. And in here we then say this dot x equals x, and this dot y equals y, for example. And you'll note that in the generated code, we just emit the code that you wrote. Now, we can, of course, also add methods to our classes. So here, let's add a distance method that says return math.square root. And by the way, here you see like all of that type information from lib.d.ts presented, right? We get not just the parameters, we also get the JS document, the JS doc comments that tell me what the arguments do. So this dot x times this dot x plus this dot y times this dot y. And now, if I say p dot, you'll see that there's a dist method that returns a number. I could also write it as a property or as an accessor just by saying get. And here you'll note that the code generation now is not quite as pretty because ECMAScript 5 doesn't actually support properties other than by calling object.define property. But in ECMAScript 6, it'll support this syntax over here. And basically, like I said earlier, we are aligning ourselves with ECMAScript 6 syntax. This syntax here is the ECMAScript 6 syntax, minus, of course, minus the type annotations, right? I forgot what I was going to say there. Okay, but so let me move along. Let's try to do statics. Static origin equals new point of 0, 0. Okay, and here if you look at the generated code, it's now starting to get a little. Well, let's not do an accessor here anymore. Let's just do a regular method. You see that we put instance variables on the instance. We put methods on the prototype. We put statics on the constructor function object. And now over here, if I say point dot, you'll see that there's an origin property now available that I declared there. And so basically, this is the kind of code that you would manually write if you were using classic JavaScript, right? But it sure is a lot nicer to be able to write it using this syntax. And I do think ECMAScript 6 is going to offer a lot of these features, but that doesn't mean that these features are going to be available on all your execution targets for a good long time, right? It's going to be years before there are enough browsers in the wild that you can actually assume that your execution target is ECMAScript 6. And one of the things that we do, for example, or that's what I was going to say, if you write here like an accessor like get this, then if your output target is ES3 or ES5, we'll generate, well, if it's ES3, we'll give you an error because ES3 doesn't even have defined property. If it's ES5, we'll generate that. If it's ES6, we'll just generate that. So from a single source, depending on what features you use, you can actually just choose yourself what you want to target. The playground currently just ECMAScript 5. It's just hardwired to do that. The playground is not super sophisticated, so we could beef that up, but yeah, it just assumes ES5. Okay. Another thing, let's try to add a private field, say color here, and then say this dot, oops, color equals red. Like so. And you'll note in the output code, we didn't do anything special for private because there are no private fields in JavaScript and there's no cheap way to do private fields in JavaScript. However, statically, we can certainly check. And out here, you'll see there is no color on P. It only exists inside the class. We also support protected. And now in a subclass, you'd be able to access color. But not outside a class declaration. So we do the best we can, which is we statically verify that you don't use this private field, but in the generated code, we optimize for efficiency. Now, as enough ES6 targets mature out there, it is possible to do this with symbols in ECMAScript 6. but currently none of the VMs implement it efficiently, and you pay too high of a cost to access these properties. So we're sticking with this for now. Okay, let me show also you know, some syntactic sweetness that we have. This pattern of declaring some properties and then having them as parameters to your constructor and then initializing them inside the constructor is so common that we sort of capture it and allow you to just say public on constructor parameters or protected or private. And then we turn them into automatically initialized properties. We also support some of the other things that are coming in ECMAScript 6, like default parameter values. So I could say this guy's default value is 0 and this guy's default value is 0, 2, and then we'll inject a check for whether it was undefined, and if so, initialize it with the value you gave. And now the type checker understands that these parameters are optional, and so I don't have to specify them, and I don't get whined at by the checker. Okay, let me see where we are on time. I'm not going to show you inheritance. Trust me, we support inheritance. Well, okay, let me just write class point 3D extends point, and you'll see now that we then emit a super call, blah, blah, blah. Here, this is the only place where we will inject code that you didn't write. Here, specifically, there are 4 lines of code that we will emit, a little helper to create a superclass or a derived class. But other than that, we never inject any code, and like I said, we have no runtime library. It's just the JavaScript that you wrote. And of course, in a derived class, you can override methods and call super and blah, 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 all of that stuff. Another pattern that's common in JavaScript is modules or root namespaces, if you will. Like think of the dollar namespace in jQuery, underneath which are a whole bunch of properties, right? That's often done by writing a function that you execute once, and you in there reveal an object with a bunch of properties and callbacks on it, and then you assign that to some global variable. And we sort of capture that as a pattern. So I could say module utils, and then put everything in here into that module, like so. And whoops, let's just scroll this guy up so you can see it all. And now if I then export the class, notice when I say export, that we then create a property on the object that you wrote inside the function closure. And now I can say var p equals new utils dot, and here we see there's a constructor function for point, et cetera, et cetera. So this is how you get to namespace your code, and we can sort of follow along and actually understand the structure of it. Modules are open-ended. I could actually write in another file, another module utils, and then add more stuff in here, and the two merge together. You'll see in the code that we generate, well, actually now that it's empty, let's say export var x equals 5. You'll see that we generate 2 of these guys, and the first one gets to initialize, the other one just adds to the one that the first one created. Oh, export, sorry. Export, oh, var x, there we go. There you go, yeah. Okay. So that's a kind of module we call internal modules. We also support external modules, which are the kinds of modules used by Node.js and Require.js. You guys should use Node? Show of hands, yeah? Yeah? Okay, a bit. Yeah, I would assume you do, yeah. Okay. Let me show you what that looks like. In fact, let's go back to the IDE here, and let's try to open up demo/node, and let me first write a little Node server, and then afterwards write a little Node client module that uses the server module that I just wrote. So what I'm going to start by doing is I'm going to reference the node.d.ts declaration file. If I go to jump into it, you can actually see in here all of the type definitions for all of Node's standard modules, and of course you can add more to that. But that sort of gets me set up to write code. The next thing I'm going to do is I'm going to import the HTTP module from Node and then write a little HTTP server. Here the IDE complains that you can't use external modules unless you use a compiler flag that enables them, but just forget about that for now. Then I'm going to write export function create server port colon number comma message colon string, like so. And then in here I'm going to say HTTP dot, and now you see statement completion on Node, right? And Node's create server takes a callback that is given a request and a response object. So declare those, and then I get to write my code in here. And again, if I say response dot, you'll see that we actually know what the type of that is, because we know that HTTP came from the HTTP module, and it has a create server method, and create server takes a callback that has a request that is of type server request and a response of type server response, so we can give those types. And so the types flow quite a bunch here, and you actually really typically end up only writing type annotations for parameters, and then you write some interface declarations, and that's typically, or classes, and then the rest just flows. So let me try to fill out the body of this guy here. There, and then let's start the server by calling listen. Listen. I'd note here that listen has 3 overloads, and we actually know what those overloads are. So we'll pick the last one here and call it with the port number that was passed in. And that's our little server module, so I'll save that. And then let me open another blank file, hello, and then let's try to write a client that uses it. So I'm going to start by saying import server equals fire of dot/server, like so. And now when I say server dot, you'll see statement completion on the server that I just wrote, right? So 1337 here, comma, hello, Google. And then console log of listening on 1337, like so. There, done. So those are my 2 little modules. Let me go to the directory where I put them, and then let me just try and compile them. And I'll just compile, and I'll actually just say compile hello. And oops, yes, I still have to spell modules. And I'll say I want them compiled for common JS modules. And the compiler automatically finds all of my dependencies here. So if you look now, what happened, it actually compiled both files. It produced hello.js and server.js. If you type server.js, you'll see that that's pretty much the code I just wrote, minus the type annotations, right? And if you type hello.js, it is exactly the code I wrote because I had no type annotations. And now if I run this, so say node hello, and then go here and go to localhost 1337, there, my little server is up and running. So that's you know, pretty simple to use Node with TypeScript. The 2 really fit together very nicely. Okay, other thing I could show here is what the experience of starting with a JavaScript project is and then upgrading it to use TypeScript. Let me close this stuff out and let me open a project here called AudioScope. This is sort of a silly little app that has 3 JavaScript files in it. And if we try to run it, you'll see what it what it does. It allows me to view WAV files graphically, basically. Now, let's say I wanted to convert this to a TypeScript project. Since JavaScript files are basically TypeScript, I could actually do that just by renaming all of these files in here to .ts instead. So let me try and do that. So I'll just call this guy ts, and it says, sure, that's fine. Then it offers up if you want to add some additional packages. I'm just going to say no to that. Let's rename this guy also. Yep. And this guy here. There we go. There. Let me actually also just close the solution and reopen it again, because sometimes in this latest version it gets a little funny. There. Okay, so now I have the same solution, but now all the files are .ts files instead. And you'll note that I get some errors here. And we could go look at what is it that the type checker is complaining about here. If you go look at default.htm, you'll see that in here we just have a canvas element and a selector element. And if you go back to the application, we do get element by ID of file select, and the compiler here infers that file list is of type HTML element. But it's actually an HTML select element that has additional properties that we can't really guess. Well, we could theoretically by looking at the HTML file, but that's sort of beyond what the TypeScript compiler does. But here I can then go in and add a type assertion where I just say, trust me, it's an HTML select element. Yeah. All right.
Tell me that.
So a cast is less strictly typed. It says one of the types has to be assignable to the other. So as long as there's a relationship between them, either that the one you're casting to is a supertype or a subtype of the other. But if you're going sort of across where you have two things that are known to be completely incompatible, then we still complain. But so it's sort of a weaker check, if you will. So I could do that in here. Also, I have the same thing going on in my audio file. I get the wave view, which actually is a canvas element. So if I add a type annotation here for a canvas element, you'll see that I silence all of my errors except for one, which I put in there just to make sure it was there. Someone had a typo here, right? And this is one of those that, and we find, when people do this, they will, and they swore they had unit tests that checked this, but it turns out that this one only shows up if you have 8-bit sample rates in your WAV files. And I guess the unit test didn't test that, right? So if we try to run, you'll actually see that bug is in there. And if I click on a file that I know is 8 bits, then boom, it blows up. But perhaps there just wasn't a test for that, right? So now we can go fix that bug. And now we are sort of in a gradually typed state. We have types for some things, but not for everything. For example, the WAV file here is typed as any, and that means here I could misspell the data property, and I would not get any errors because we don't know what it's. Now, one of the ways you can tighten the screw, so to speak, is you can compile with an option. Command line compiler has an option called no implicit any. And I'm going to turn that on. And that really just says, okay, let's tighten down the hatches here and disallow any forms of untyped variables. And now you start to get a bunch of errors. And now you have to go stamp those out, right? So to speak. And I could do that in my project here. For example, here I would likely, for this guy, I would instead declare an enum. For this constructor function, I would declare a class. For these two guys here, I would add type annotations to the functions. And finally, down here, I would have type annotations on these parameters. And as I do that, the errors gradually go away. I still have a few remaining over here that I could stamp out. So I could make this into a WAV file, and then this scale point here, I know that it's a number. And now I've actually killed, well, all but the last build error there. So now I know with certainty that everything has a statically known type in here. And that now means that refactorings are safe in this code base. And now I can go to work and maybe I've for the longest time been wanting to change this data property here to be called wave data or whatever, right? Now I can safely do so. Call it wave data. And if you go look at where that you see here that we now know where to go change this in, and this happens in files, and it happens safely. And the type checker will tell you whether or not it works. And that's, I mean, that's really sort of one of the very, very big value propositions that this system brings, because as you get into the really large code bases, and let me try to show you a really large code base, the TypeScript compiler itself. Oops. So let me try to, well, actually, let me close that project. And let me just open the command line driver for the compiler. So the compiler, TypeScript compiler is about 22,000 lines of code. And then on top of that, there's about 8,000 to 10,000 lines of language service code, you know, the code that implements refactoring and whatever. And all of that is actually part of the repository. So all of the support that you need to plug into an IDE is part of the TypeScript distribution. Now, this guy here, we could sort of try to look at how the compiler works. It sort of starts by executing a command line. And now I can, because we have static typing, it's super easy to navigate around. I can just say, go to definition of execute command line. It shows me where that is. That guy calls my compile method. I can go look at that. The compile method, in order to type check, ultimately creates calls get type checker. If I go to that, we see, oh, but that's implemented in an interface. But then I could say, oh, well, show me all of the uses of this guy. And here instantaneously in 22,000 lines of code, where is this guy used? And so here, for example, is the actual thing that implements that interface and creates a type checker. And I could go look at all the places that's used or go to its definition and so forth. So the code is pretty easy to navigate. It's not a very huge code base, but it's still sizable. But let me show you, let's, for example, go to, let's say a check if statement. Here's the function that type checks an if statement. And you note that it first checks the expression that controls and then the then and the else part of the statement. If we go to definition of this on this guy, you'll note that this is just declared as an object that has these three properties. I could go back and I could say, well, show me all of the places that this guy's used. And here you see all of the places it's used in the checker, the emitter, the parser, et cetera, et cetera. Now, you'll also note that there's another expression node up here on expression statement, but that's a different property. And I could actually safely just right here say, you know, I want to call this condition instead. And you'll note that it changes that one and all of the places that it is referenced in turn, but it didn't change this guy up here because we know the difference between the two. And this is something on a daily basis we refactor like that, and it would just be hell on wheels without it. Okay, let me undo that one. Let me just sort of, as a final thing, show. Yeah, go ahead. Right.
So,
Sure. So we do it. It's sort of. Yeah. Okay. So the question is, if it's all structural, how can you tell, you know, like whether that one implements the interface? Well, so we cheat a little bit there. You know, we can actually also trace the nominal type implementation tree. So we can say all the places that says it implements that interface, those we will go change. All of the places where a variable has that type or gets implicitly typed to that type, we will go change. So, you know, once we have all the static knowledge, we can do a pretty good job of it. I wanted to just show, compiler here. Maybe just sort of compiling the compiler itself. I'm just going to compile it into xxx.js. But then I'm going to ask it to also generate a declaration file. Now, one of the things that's whoops. Oh, I forgot to say dash out xxx.js -d and then compile tsc.ts. And that compiles the whole compiler and then generates, and that's 22,000 lines. I mean, it's pretty fast. It also then, it produced two files here. A JavaScript file, which is the entire compiler, which actually consists of 10 files that it automatically traced down because we know from references between files. But then I also asked it to generate a declaration file. And this actually sort of becomes a synopsis or a .h file for the compiler, if you will. And if I open that one, you can see that in here is all of the exported types in the compiler. So as you're building projects in TypeScript, you can basically build the implementation or the binary, if you will, which is the JavaScript, and you can build the H file that you give to the consumer of your library. And we can automatically produce both of those. And that's super handy. Okay, that's sort of my 1 hour overview. Maybe I'll just go back and just briefly summarize here. Whoops. So, as I mentioned, the TypeScript, the type system, the way to think of TypeScript's type system really is that it's a highly accurate static representation of JavaScript's type system, because even though JavaScript is a dynamically typed language, it actually has a type system with semantics that can be statically modeled. And then that's what we do here. But one of the things that's interesting about it is that we do it sort of from a different vantage point. Traditionally, type systems have either been entirely off or strictly checked. And we're, in a sense, instead of having a switch that turns types on and off, we have a dial. You can set the dial where you will. You know, you can be gradually typed more and more. And the more you turn up the typing, the more benefits you get. And if you turn it all the way up, then you get things like safe refactorings and so forth. So that's sort of the way we think about types in TypeScript. As I said, we provide polyfills for a bunch of things, including modules. And we are committed to also supporting ECMAScript 6 modules, which have a different but not ambiguous syntax with what we currently support. So ultimately, we'll support both Node, Require.js, ECMAScript 6, and internal modules done as executing functions, revealing, and so forth. We have a pretty active community hub, and we have we're starting to see a lot of people take dependencies on TypeScript now. Mozilla has an interesting project called Shumway, which is an implementation of a Flash player entirely written in JavaScript and HTML5. It's 170,000 lines of TypeScript, and that's on GitHub. There are several popular gaming engines, JavaScript game engines. I think a lot of JavaScript games used to be written in Flash, and a lot of these people are moving to TypeScript because Flash and ActionScript actually already had classes and rudimentary type annotations, and this is in a sense just a move into the standards world for those people. There's an interesting, crazy project called Doppio, which is a complete implementation of a Java VM written in TypeScript that compiles to JavaScript, and it's amazing. You literally boot up Java in your browser. It's nuts. I talked about the frameworks. On DefinitelyType, I think we're even above 700 now, library definitions, very, very active community there. And we're seeing a lot of support in tools. Of course, I showed you Visual Studio here, but there are plugins for Eclipse, WebStorm. Actually, the JetBrains guys do their own type checking and whatever, but using TypeScript syntax. Sublime Text has a plugin. There are various build systems and so forth. So right now, what's out publicly released, we just released yesterday TypeScript 1.3 in preview of Visual Studio. We're actually in-house currently almost done with TypeScript 1.4, which will have union types, let and const, template strings, symbols, etc. 1.5 will have destructuring, and so we're just sort of checking off all the ECMAScript 6 features, and ultimately next year we'll arrive at ES6 parity with down-level support where it's deemed feasible. Certain things we can take down level meaningfully, other things we cannot, like let and const. You can't really take it down level with the semantics of let and const, so we probably won't. And then we have like some stretch goals. We'd love to do async await, which if you assume ES6 is easy because you can build it on top of ECMAScript 6 generators. But if you want it down level, it gets trickier because you have to do some very gnarly source code transformations to turn function bodies into state machines, and your code looks nothing like what you wrote after we're done with it. So, and then that it has sort of been our mantra to generate beautiful code, and it's not beautiful. so we're mulling that one over. But it may be that, given that we support source maps and whatever, it may not be an issue. That's pretty much it.